Now we're going to look at continuity at a point and what that means. So continuity, as I said before, is any line that has nothing interrupting it, nothing stopping it, any line that you can draw without picking up your pencil at all, right? So in calculus, in the next part of this unit, they give you a specific mathy definition that's given right here. You know a function is continuous when f of a is defined, when limit f of x when x approaching a exists, and when limit f of x approaching a, and f of a are the same. What does this mean? F of a is defined just means that your function, your line, exists. Like, it's there, it exists if it's within the criteria of whatever restrictions they give you. The limit f approaching a exists. That just means that from the left and the right side, if you look at every point, you look from the left and the right side, they agree, right? In a function, the limit of every single point needs to exist for a function to be continuous. And the last one, the limit of any x value has to equal the point on the graph of that x value. So an example of that is, like, if you have a line like this, but there's a hole here, and your actual x point is up here, even though the limit exists, right? It's not the actual point, so this counts as non-continuous, right? So the limit and the actual points of every point on the graph has to exist as well. So let's look at this example to see if this function would be continuous at, let's say, x equals 5 and x equals 6. So if we look at the three criteria, f of a is defined, f of x is defined here, so this meets the first criteria. Okay, the second one, f of x exists, right? Okay, so to see if the limit exists for x equals 5, you're going to have to plug it into these first two equations, because that's where 5 will be on the graph. So anything less than 5, you're going to use the top equation, and in between 5 and 6, you're going to use the middle equation, right? But to see if they meet up in the middle, you're going to have to look at the left limit, and you're going to have to look at the right limit to see if they agree with each other. So to find the left limit, you're going to use this left equation here, because this is the left of 5. And you're going to plug it in, you're going to get 4 times 5 plus 7, which is 20 plus 7, so you're going to get 27. And for the second one, x squared plus 2, if you plug in 5, you're going to get 5 squared plus 2, or 25 plus 2, and you're going to end up with 27. So limit f of x exists. And f of 5, in this example, you're going to use the top function because this is less than or equal to 5. So when x equals 5, it's going to be 27. They're both 27, doesn't matter. So you know that at 5, this graph is continuous. And you could show all the criteria, and you can see that since the left limit and the right limit agree, at the point 5, this function is going to be continuous. Okay, and look at this on the right, x equals 6. What would you do here? Y'all could try to solve this. Y'all could pause it right now. Okay, so we're going to go over it. So x equals 6, f of a is still defined, like nothing changed. So this meets the first criteria. The second one, if the limit f of x when x is approaching a exists. Okay, well, you can see we're looking at 6 here, so we're going to look at these bottom two equations. So we'll plug it into the top one to find the limit from the left, and you get 6 squared plus 2 is 38. And if you plug it into the bottom one to get the limit from the right, f of x, you're just going to get 6 squared, which is 36. So these two limits do not agree with each other. So limit when x is approaching 6 of f of x does not exist. So it does not meet the second criteria. It also doesn't meet the third one, because if you look at f of 6, you're going to be using this equation, you're going to get 38. If you're using limit x approaching a, f of 6, it does not exist, so it's not the same thing. We're going to look at one more example of this, and then we'll move on. Okay, let's look at this example here, and we're trying to find if this graph is continuous at x equals -2. So to do that, the function is defined, the function exists, right? So it meets one criteria. We have to see if the limit at -2 exists. So plug it in, limit x approaching -2 from the left of f of x. You get 14, -2 plus 2, -28 plus 2, you're going to get -26. Okay, and you look at the right limit, it's 5 times -2, you're going to be left with -10. So these two limits are different, right? So the limit f of x of when x is approaching -2 does not exist. So this graph is not continuous. And if you try to find what kind of discontinuity it is, if you look, it's not a hole, and it's not an asymptote, right? So a graph like this at -2, from the left is approaching -26 down here, and from the right is approaching -10, right? So that's gonna be like up here. You're gonna have two lines like this, right? So since there's a gap here, this is called a jump discontinuity. We learned about it last section. So anytime it's like this, and it's like piecewise with two different points that don't agree with each other, going in two completely different ways with like a hole in it, there's a jump. I mean, yeah, that's kind of all you gotta know. You gotta know how to find a jump discontinuity, what it is, and how to see if things are continuous. We're moving on.